So join the tell me please whether you are getting the audio or not. Number 1788314.
Audio is not clear, sir.
Audio is not clear now.
Not clear. No, sir.
Now,
There is some
now it should be clear, right?
not so clear, sir.
Maybe yes, it is a proper audio. Maybe I was speaking a bit lower. Once I start the discussion, I'll be speaking at a louder pace. Everybody knows that there is a class up to 50, right?
Yes, sir.
I'll wait for a few more minutes, then we'll start the discussion. Just we'll wait for 2 more minutes till it is 2:55, then we'll begin the discussion. Okay, so it is already 2:55. So let me share the desktop and start discussing topics of today's session. So somebody can see the PDF which I shared to you now. Somebody please respond.
Yes, sir.
Okay. So in the last class we have made a discussion about so in any number system we can define two different types of complements that you usually refer to as a radix complement or the R's complement. Then we have the diminished radix complement or the R minus 1's complement. And we have seen examples for that in the case of a decimal number system and in the case of a binary number system. So how do you compute tens complement, how do you compute nines complement, and how do you compute the two's complement, and how do you compute one's complement. So these things now we are well aware of. Okay. So given any number to you, you can easily determine what is the nines complement of it, what is the tens complement of it, what is the one's complement of it, and what is the two's complement of it. Okay. Now, after understanding these complements, we went on to understand the representation of signed numbers or signed integers. Okay. So we have seen there are three representations for in negative number representations. Okay. So these are the first one is referred to as the signed magnitude representation. The second one is referred to as signed magnitude, signed one's complement representation, and the third one is signed two's complement representation. Now we have this understanding of given a number which you want to represent in a negative number. Now you can easily represent this negative number in any of these three representations. I hope that idea or that concept is clear to you. So given any number which you want to represent a negative number, you can easily represent it using it the three different forms there: signed magnitude form, signed one's complement form, and signed two's complement form. Okay. So is that concept clear to you guys? Somebody please talk to me. Is that concept of negative number representation clear to you?
Yes, sir.
Any doubts there? Anybody has any doubts there in the discussion? Yes, guys? No doubts? So, and we have seen how the signed two's complement representation can be used in performing some binary arithmetic. Okay. So let us take the discussion forward and try to understand a few more things about signed representation. Okay, we have seen binary arithmetic, how it can be done using signed representations. Okay. Now going further, the last class we ended with this small table here, where I represented 4-bit signed binary numbers in different representations. So this table is illustrating you how can you represent a 4-bit signed binary number in the three representations which you have understood: signed two's complement form, signed one's complement, and signed magnitude form. So what you observe from this here is, please look here. So whenever you are talking about zero, if you look at this table, 0 has only one representation in the signed two's complement. Okay, 0 has only one representation in signed two's complement. But when you look at the representation for 0 in the other two systems, other two representations there, we have a positive 0 as well as we have a negative 0. So that there are different representations for positive 0 and negative 0. So that is an important observation you need to make here. So 0 has a single representation in the signed 2's complement representation format, whereas it has a positive 0 and negative 0 in the signed 1's complement and signed magnitude representations. Okay. So that is the reason why normally whenever you are doing arithmetic at the binary level, we do not go for these approaches. Okay. So we go for the signed 2's complement representation only, normally. Okay. Then what you observe is if you see the negative numbers here, -1 to -8, all the negative numbers in all the representation, the most significant bit is always 1. So -1, the most significant bit is 1. You sign 2's complement. If you look at sign 1's complement also, the most significant bit is 1. And even if you look at sign magnitude representation also, the most significant bit is 1 there. So that these are some inferences we draw from this table. So sign 2's complement representation has only one representation for 0, which is always positive. The other two systems, that is sign magnitude and sign 1's complement, has positive 0 as a negative, as well as a negative 0, which is not encountered in ordinary arithmetic there. So that is the reason why whenever you are doing arithmetic at the lowest level, usually sign 2's complement representation is followed. And all negative numbers have a 1 in the leftmost bit position, indicating that it is a negative number there. So these are some inferences or some observations we make from this table here, which is illustrating the possible representations of a 4-bit signed binary number. Okay, so please go through this table once I share this PDF on the Teams there, and try to observe the inferences I am making from this table here in the form of this note here. Okay. Now going further, let us understand how we can do arithmetic using signed 2's complement representation. Okay. Now say for example, I have this operation +6 + 13. So how this operation occurs at the binary level? Let us try to understand that. So can somebody tell me what will be the answer for this? So I am adding two numbers. One number is +6, the other number is +13. So what is the result you expect? What is the result you expect, guys? Anybody, please respond. What is the result you expect here? Anybody? I'm adding +6 and +13. What is the result you expect? Guys, please respond, Mike. What is the result you expect? The result would be positive 19. Agree? Agree?
Yes, sir.
Now, so how it is done actually in the machine? Okay, let us try to understand this. So the first number, if you observe here, it is a positive number. So here I am using an 8-bit representation. So whenever I am talking about an 8-bit representation, can somebody tell me how do you represent this +6 using 8 bits? So as it is a positive number, the most significant 4 bits will be 0, followed by, as it is 6 here, the representation will be 0, 1, 1, 0. Is my representation correct there? +6. Yes? Now, now let us look at the other number, which is +13. So how do you represent this +13? As it is once again a positive number, I can represent it to something like this. 4 zeros, no significant bits there. And 13 is 8, 4, 0, 1. Is this 13? 8, 4, 12, 12 plus 1, 13. So I am using the 8, 4 to 1. You observe, so this is the binary representation of 13, 1, 1, 0, 1. Am I clear? Am I clear till this point? Guys?
Yes, sir.
Okay. Now, so how do you add? Just you simply add the binary bits there. So 0 plus 1, 1, 1, 1, 1, 0 here, 0 here, 0 here, 0 there. Can somebody tell me what is the value of this binary number which you got? So you place the place value here, 0, 1, 2, 3. Then what you do? 1 into 2 cube plus 1 into 2 square plus 1 into 2 power 1 plus 1 into 2 power 0. Do you agree? So the value of this number is what? 2 cube is 8 plus 2 power 4 is 2 square is 4 plus 2 plus 1. So what is the value of this? 8 plus 4, 12, 12 plus 2, 16, 16 plus 1.
So you have to take that carry, sir. 1 plus 1. 1, 0.
Yeah, for 1 is carry. Yeah, you are correct. So here it will be 0 and here it will be 1 more. So in that case, 1 more 1 into 2 power 4 will come into the picture, right? Am I correct? Am I correct? Huh? Am I correct, guys?
So near third bit also, sir. 1, 0.
I made a mistake. So let me do it once again. So I'm adding, so the first thing is the binary representation is correct, right? Is the binary representation correct? Now let us do the addition once again. 1 here, 0 carry 1, 0 carry 1. So this will be 1 here, this will be 3 zeros, right? Now it is correct? Yes, somebody? Is this correct now?
Yes, sir.
Yes,
Now
sir.
once you place the base value 0, 1, 2, 3, 4. So if you expand it, the value of this number will be 1 into 2 power 4 plus 1 into 2 power 1 plus 1 into 2 power 0. Where I am ignoring these two zeros here. So in that case, what is the value of this number? 16 plus 2 plus 1. So it is 19. So this is done internally. Okay. Am I clear with this small process? Yes, guys? Yes, guys, am I clear? Am I clear? Okay.
Yes, sir.
Yes, sir.
Okay. Now let us proceed further. I have minus 6 plus 30. I have to do this operation minus 6 plus 30. What answer you expect here? What answer you expect here? What answer you expect here? Plus 7 or minus 7? Plus 7 or minus 7?
Plus 7.
Plus 7 you expect the answer. Okay. So how is it how this operation is done internally by the system there? Okay. So let us look at this first number here. This first number is minus 6, right? So what happens? You have to represent it since it is a negative integer here. You have to represent it signed to 2's complement form. Okay. So in order to represent this negative number here plus minus 6, what you do is first represent plus 6. So what is the binary representation of plus 6 using 8 bits there? It will be 4 zeros followed by 0, 1, 1, 0. So this is plus 6. Then if you want to represent the signed 2's complement of plus minus 6, signed 2's complement of minus 6, that will be equal to what? Take the 2's complement of this entire binary pattern, right? So if you take this signed 2's complement of this pattern here, so the procedure says leave all the subsequent zeros unchanged, the first zero will be as it is. Then any 1 is coming, that 1 is also left over as it is. Remaining all should be complemented. So 1 becomes 0, 0 becomes 1, 1, 1, 1, 1. So this is the representation of minus 6 in signed 2's complement form. Do you agree, all of you guys? Do you agree? Do you agree? Any conflicts there? Any conflicts there?
Yes, sir.
So this is the signed 2's complement of minus 6. Now what we do, what the system does is, wherever minus 6 is there, it will replace minus 6, it will replace this minus 6 with this signed 2's complement representation. Okay, so it will put 4 ones followed by 1, 0, 1, 0 for minus 6. Okay, then to that I am adding 13. So 13, all of you know how to represent 13, right? 13 will be simply 4 zeros. 13 will be as it is a positive number, 4 zeros followed by 1, 0, 1, 1. Do you agree? So this will be 13 in signed representation. Okay. So 4 zeros followed by 1, 0, 1, 1. This will be 13. Agree? So add these two binary numbers.
Sir, 1101.
13, right? 1101, sorry. So it should be 1101. So So 1101. Okay. So let me erase this also. So it will be 110. Okay. Now just add these two binary numbers. Okay, this will be 1 here, this will be 1, this will be 1, this will be 0, carry 1. Okay. Now this will be 0, carry 1. This will be 0, carry 1. This will be 0, carry 1. So this will be 0. Now there is an n carry which is generated. Okay. So whenever you are doing binary arithmetic, the procedure says whenever there is an n carry, just simply discard it. So whenever there is an n carry generated, simply discard it. And what is the answer you got? What is the answer you got? It's a binary representation of plus 7. Do you agree? So is my answer matching with this answer which we have represented here? This is how the system does it internally. Am I clear? So it discards whatever last n carry is generated, that n carry discards, and whatever is remaining in the result, that forms the answer for us. Am I clear this procedure? Am I clear, guys? How
Yes, sir.
arithmetic operation is performed? Now let us look at one more operation. I have minus 6 plus 30. So let us have minus 6 plus 30. Third case, minus 6 plus 6 minus 30. So plus 6 minus 30. First number is plus 6, positive 6 minus 30. So what answer you expect here? What answer you expect here, guys? What answer you expect here? Please respond, guys.
-7.
-7.
So it will be minus 7, right? No. So the first number being a positive number, plus 6 is represented something like this in binary. Okay? So 0, 1, 1, 0. Now come to minus 30. As it is a negative number, first we should look at the representation of 13. So 13, how is it represented? 0 and 4 zeros followed by 1, 1, 0. This is 13. Okay? Then to represent the sine 2's complement of 30. Sine 2's complement representation of minus 13. So what will be that? What will be that? This will be the 2's complement of this plus 13, right? Do you agree? Sine 2's complement representation of minus 13 will be sine 2's complement of this plus 13 value, binary pattern. You are following the discussion? Yes? So this will be 1 here. This will be 1. This will be 0, 0, followed by 4 ones. Is this correct? Is the sine 2's complement representation of minus 13. Am I clear in this point? This is how you represent minus 13. This is how you represent minus 13 in sine 2's complement form. Am I clear till this point? Yes, guys, please respond.
Yes, sir.
Now, so once we have this representation, now plus 6 can be represented as 4 zeros followed by 0, 1, 1, 0. Now minus 13, I have to use the sine 2's complement representation. Therefore, it will be 4 ones here followed by 0, 0, 1, 1. Okay, this is the sine 2's complement representation of minus 13. Now add the numbers there. 1 here, 0 carry 1, 0 carry 1, this 1 here, this 1 here, 1 here, 1 here, 1 here. Now is there any n carry generated? There is no n carry generated. No n carry generated. So in that case, what will be the answer? In that case, what will be the answer?
Negative of 2's complement.
Negative of 2's complement
Complement of answer.
of whatever result we got here. 2's complement of 4 ones followed by 1, 0, 0, 1. Can somebody tell me what is this value? 2's complement of this? The first one will keep it as it is. 1, 1, 0, 0, 0, 0, 0. Am I correct here? So what is this minus of this binary pattern? What is the value of this binary pattern? Minus of what value?
7.
So this is how the operation is done internally. This is how the operation is done internally. As there is no n carry generated here, the actual answer will be the negative of the 2's complement of the result of the operation which you got here. Okay, which is minus 7 as listed. Is my discussion clear to this point? Guys, please respond.
Yes,
Is the
sir.
discussion clear? Okay. Now let us proceed further. Take one more scenario. Minus 6 minus 30. Minus 6 minus 30. In that case, what will be the answer? What answer do you expect?
-19, sir.
Minus 9. Now, can somebody tell me the representation of plus 6 in binary? So, as both the numbers are negative, first we'll look at the positive representation of plus 6. So, plus 6 is what? 4 zeros followed by 0, 1, 1, 0. Now, minus 6 would be what? 0, 1, 0, 1, 1, 1, 1, 1. This is minus 6. Do you agree? What is this representation? 2's complement representation. Agree? Agree?
Yes, sir.
Now,
Yes, sir.
similarly,
Yes,
I have to consider the other number, plus 13. Plus 13 means 0, 0, 0, 0, 1, 2, 0, 1. This is plus 13, right? Now minus 13. Minus 13 will be, take the whose complement of this binary pattern. Okay. So that will be 1. This will be 1 here, 0, 0, 1, 1, 1, 1. This will be the whose complement representation of minus 13. Whose complement representation of minus 13. Am I clear till this point? Am I clear till this point? Now, so we have to perform this operation, minus 6, minus 13. So what we do, minus 6 you represent using the sign to square representation. That is, I represent it as 4 ones followed by 1, 0, 1, 0. Now minus 13 you represent using sign to square representation. That is 4 ones followed by 0, 0, 1, 1. So you add. This will be 1 here, this will be 0, carry 1. So this will be 1 here, 0, carry 1, 1, carry 1. 1 carry 1 and this will be 1 carry 1. So in that case, what happens? Is this correct? Yes. So in this case, what has happened here? In this case, what has happened?
One as
So there is an n carry generated. So whenever there is an n carry generated,
Discard.
discard it. So discard it. And what remains is the answer. What remains is the answer. But the answer is in what form? As it is a negative number, the answer is in the 2's complement form. So the answer is what? The actual answer is what? Negative of. So what is the actual answer? The actual answer is negative of this number. Do you agree?
yes, sir.
So what will be the answer for this? Take the 2's complement of this. 2's complement will be 1, 1, 0, 0, 1, 0, 0, 0, right? Negative of this value. And what is this value? Negative of this value. What is this value? Binary value.
19.
Minus 9.
19.
Minus 9. Okay. So since here, after doing the operation, we see that the most significant bit is 1 here. That means that the answer is the negative number. So whenever we say that the answer is the negative number, by saying the most significant bit there, we observe that you can obtain the answer by taking the 2's complement of this result which you got. Okay. So that will be, you just put a minus sign and just take the 2's complement of this binary value, that will give you the answer. So this is how the system understands arithmetic at the lowest level. Am I clear to this point? Am I clear, guys?
Yes, sir.
Now, after understanding these things, let us proceed further and try to understand what are binary codes. Okay, so we are all dealing in our discussion of digital electronics and the logic design. We are dealing with basically information, and in this information is nothing but a group of quantities which can be represented by some binary code. Okay, so why we only want binary codes? Because the machine only understands ones and zeros. Okay. So any information you want to represent, that has to be represented in binary, in the form of binary codes. Okay, always. Why? Because the machine will not understand anything, but it will only understand ones and zeros. So that is the reason why we should know the various binary codes you can use for representing various information quantities. Okay. So, so if you have n bits, so if you are using the 2 bits, say for example, if you are using only 1 bit. So this 1 bit can take how many combinations? This 1 bit can be either 0 or 1. So in this case, these are the possible binary codes using 1 bit. The possible binary codes using 1 bit. Do you agree? There is only 1 bit. This 1 bit can be either 0 or 1. So this is possible binary code when you are using only 1 bit. Am I clear? Am I clear? Am I clear? Guys, please respond.
Yes, sir.
Now, say for example, I use 2 bits. So in that case, how many possible combinations you can have? 2 for 2. That is 4 possible binary combinations you can have. And what can they be? What can they be? 2 bits. So 2 bits can be either 2 zeros. One of them can be 1, the other one can be 0. Or one of them can be 0, the other one can be 1. Or both can be 1. So whenever you are using 2 bits, the possible binary codes can be 0, 0, 0, 1, 1, 0, 1. Do you agree? So whenever you are using 2 bits for binary representation of an information, so the possible binary codes can be 0, 0, 0, 1, or 0, 1, 1. Am I clear? Am I clear till this point? Am I clear till this point? Somebody please answer.
Yes, sir.
Now say for example I use 3 bits to represent the binary. So how many possible combinations you can have? When I use 3 bits, how many possible representations you can have for binary codes? Yes,
8.
8 2 cube. That is 8 possible binary codes. What are they? What can they be? It is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and finally 1. So these are the possible 8 combinations whenever I am using 3 bits for representing the information. So I can use this for one element of information. First element of information. I can use this binary code for the second element of information. Okay, like that. Depending on how many bits you want to use, I can represent so many elements of information using those bits. Okay. So this is one way of using the binary code for discrete elements of information. Am I clear to this point? Am I clear to this point? Yes. Am I clear, guys, to this point?
Yes,
So,
sir.
so depending on the
Yes,
number
sir.
of bits, you are using for the representation, you can have those many possible combinations. So finally, if you want to calculate, say for example, I am using n bits for representing the information. So what are the possibilities you have? So I am using n bits for representing numbers. So how many possible combinations you can have? How many possible combinations you can have? Anybody?
Or
2 for n possible combinations, binary representations. Right? Now, so in this case, so an n-bit binary code is a group of n bits that are sum up to 2 power n distinct combinations of 1 from 0. Now you understand the statement here. An n-bit binary code is nothing but a group of n bits that are assumed up to 2 power n distinct combinations of 1 from 0. Am I clear with the statement now? Am I clear with the statement now? Yes or no? 3 bits we have seen. So 3 bits, there are how many possibilities? 2 power 3, 8. And we are saying just now, what are the 8 possible binary combinations? These are my 8 possible binary combinations, right? So that is what I am saying here. For an n-bit binary code, we have n bits together that can assume 2 power n distinct combinations of 1 and 0. Okay. So a set of 4 elements can be represented with a code of 2 bits. So if I have a set of 4 elements, I can represent these 4 elements using a code of 2 bits as 0, 0. The first element can be represented with the binary code 0, 0. The second element of the set can be represented using the binary code 0, 1. The third element can be represented using the binary code 1, 0. And the fourth element can be represented using the binary code 1. Am I clear to this point? Yes?
Sir, your voice is low, sir.
My voice is low?
Yes, sir.
not clear.
So in this way, depending on the number of bits you are using for the representation, depending on the number of bits you are using in the representation, I can have so many binary combinations there. Am I clear? So if I want to represent a set of 4 elements, I can give the binary code 0, 0 for the first element of the set. I can give a binary code 0, 1 for the second element of the set. I can give a binary code for 1, 0 for the third element, and finally 1, 1 binary code for the fourth element. If you have a set of 8 elements, the first element can be presented as 3 zeros, the second element can be presented as 0, 0, 1, third element can be presented as 0, 1, 0, fourth element can be presented as 0, 1, 1, like that. Am I clear? Am I clear, guys? There is one possible binary code which you can use for identifying the elements of information. Like that, you can have a variety of different binary codes. Okay. Say, for example, 10 decimal digits can be coded with 10 bits. Okay. So the alternate way is, say, for example, I have 10 elements. Okay. I have 10 elements. Okay. Say, for example, I have 10 elements. So these 10 elements, the minimum number of bits you can represent, minimum number of bits to represent 10 elements can be what? The minimum number of elements to represent 10 elements can be what? Anybody? Just now we said 8 elements are there. So in order to represent 8 elements, how many bits are required? 8 elements in a set are there. In order to represent these 8 elements, how many bits are required? How many combinations are required? How many
Three.
bits? 3 bits, right? So you can represent 8 elements by 8 elements by 3 bits there. Now, say for example, I have 10 elements. So what is the minimum number of bits you can use for representing 10 elements? Anybody? Can you make a guess there?
What's
Huh? 4. But using 4, how many possible elements you can represent? 2 power 4 is how much? 16. So using 4 bits, I can represent a maximum of 16 elements. But to represent 10 elements, I can minimum number of bits I can use is 4. Agree? Agree? Agree, guys? Agree or not?
Yes.
Now, in that case, if I am using 4 bits to represent 10 elements, so say for example, 10, how do you represent? The value of 10, how can you represent? 1, 0, 1, 0 is 10. Where I am using only 4 bits to represent 10, right? I am using only 4 bits to represent 10. So this is a binary code for me. This is a binary code for me. 1, 0, 1, 0 is a binary code for me. For the same 10, I can use something like this. 0, 0, 2, 3, 4, 5, 6, 7, 8, 9. So, 0, 1, 3, 4, 5, 6, 7, 8, 10. So, I make this bit as 1. This bit as 1. So, there is also a possible representation of 10. This is also a possible binary code for 10. Do you agree? This is also a possible binary code for 10. Yes or no? So where I am using, whenever 0 value comes, I make this one. Whenever 1 value comes, I make this one. 2 comes here, I make this one. 3 comes here, I make this one. 4 comes here, I make this one. 5 comes here, I make this one. 6 comes here, I make this one. 7 comes here, I make this one. 8 comes here, I make this one. 9 comes here, I make this one. So if 10 is coming, therefore I make this one. So this will be 0 and this will be 0. So here how many bits are we using to represent 10? How many bits I am using to represent 10? 11 bits, right? So in this way, this is also a possible binary code for us, right? Do you agree? All my bits are ones and zeros. Therefore, this is also a possible binary code. Do you agree or not? Do you agree or not? Guys, please respond. Do you agree or not? I can represent 10 in this fashion. Do you agree or not? Please respond, guys. Guys, are you there? In the meeting?
sir? Yes, sir, but your voice is low, sir.
I'm speaking at the modest audience. So in this case, it is 10, right? So this 10 can be alternately represented by using this binary code. Where 10 is there, I am placing 1. Similarly, if at all 9 was there, I can put a 1 here at the 9th place. Okay. So that can be a possible binary code for me. So in this way, I can have so many number of binary codes possible to represent my elements of information. Okay. So to represent them, this can be one possibility, a 4-bit binary code like this. To represent the same term, this can be 11-bit binary combination like this, can also represent 10 form. So depending on the context, depending on the application, you have to choose your binary code. Depending on the context or depending on the application you are designing the problem for, you have to choose your binary code representation of the information. Am I clear with this point? Am I clear with this point there? So for 10, binary is 1010. So another binary code for 10 can be something like this. So for 6, binary code will be 0110. Another binary code for 6 can be something like this. So in this way, we can have so many binary codes for various elements of information which we have. Agree? All of you. Agree, guys? So there are a variety of binary codes available for us. There are a variety of binary codes available for us. So depending on the context of the problem, depending on the context of the application you want to design, you can choose a proper binary code for the given system. Okay, so that is the concept here. So you have to keep in mind whenever you want to represent the information, you have to keep in mind what kind of application you are designing the system for. Based on that, you can choose the possible representation of binary code. Okay. Now the other examples of binary code which we have is the next important binary code which we have is what is given as binary coded decimal. Binary coded decimal. So all of you know what are decimals. So let us understand this binary coded decimal. So decimals are numbers between, anybody? What are decimals? Decimals are numbers between 0 to 9. Do you agree? So this is also one possible binary code for us. It's also one possible binary code for us. Binary coded decimal is also one possible binary code for us. When I say decimals can take the numbers between 0 to 9. So I can represent the 0 as something like this. So I will put 0 as this. 1 I will put something like this. So 2 I will put something like this. 3 I will put something like this. 4 I will put something like this. 5 I will put something like this. 6 I will put something like this. 7 I will put something like this. And finally 8 I will put something like this. And 9 I will put something like this. So in binary coded decimal only we have like 10 numbers here, 0 to 9. So this is a possible binary coded decimal. Possible BCD representation. This is a possible BCD representation of binary coded decimal. Do you agree? Do you agree, guys? Do you agree, guys? Now I want to represent 10 in BCD. I want to represent 10 in BCD. How can you do this? I want to represent 10 in BCD. How do you do this? So, do we have any number called 10 in the binary coded representation? We do not have. The numbers in binary coded representation, BCD representation, we have numbers only from 0 to 9. But I want to represent the number called 10 in BCD. So, how do you do that? So, what you do is every digit you represent with the binary code. Okay. So, this will be 1 and this will be 0. So, 10 in binary BCD will be this. 10 in binary coded decimal is this. Do you agree? Are you following the discussion, guys? Guys, are you following the discussion?
Yes, sir.
Now, say for
Yes,
example,
sir.
I want to represent 16 in BCD. What can be that? You want to represent 16 in BCD, but how can you represent that? So 16 means this one is something like this. 16, 6 can represent as 0, 1, 1, 0. This is the BCD representation of 16. BCD representation of 16. Do you agree? Do you agree?
Yes, sir.
Okay. So the other important binary code which we normally use is binary coded decimal. So this is how we represent binary coded decimals. Right? Am I clear with this point? Am I clear with this point?
Yes, sir.
Now, after understanding how do you represent the binary coded numbers, okay, take one more small example. Now, say for example, I want to do the BCD addition of 4 and 5. So now we are doing BCD arithmetic. BCD addition. So I want to add BCD 4 and 5. So all of you know what is the result of the operation, plus 9. So how do you do that in BCD? So what is the BCD representation of 4? What is the BCD representation of 4? Anybody? 4 can be represented in BCD as 0, 1, 0, 0. Do you agree? Similarly, 5 can be represented as 0, 1, 0, 1. Do you agree? Now just add these two BCD numbers. Okay. This will be 1 here, 0 here, 0 carry 1. This will be 1 here. So what is this? What is this? 1, 0, 0, 1. What is this? Is it the BCD representation of 9? Is it the BCD representation of 9? is the answer which you got here, the BCD representation of 9. Agree or not? Yes or no?
Yes, sir.
So this is how you do BCD addition. Now take one more example. 4, 8. Say I want to do this operation plus 4 plus 8. What is the answer you expect? Plus 12. Now how do you do? Represent 4 in BCD. 4 in BCD is this. Represent 8 in BCD. So 8 in BCD is this. Just add them. 0, 0, 1, 1. So what is this? What is this? What is this? Anybody? What is this value you got?
12, sir. 12.
It is 12. It is 12 in what code? It is 12 in BCD code.
Binary representation.
So it is 12 in binary representation. Please understand here. It is 12 in binary. But what we are doing BCD arithmetic. So what answer you expect here? We expect the answer to be in this form, right? When I want to 12 in BCD, it should be something like this, followed by 0, 1, 0, 0, 1, 0. Something like this should be the answer. This should be the answer I should get whenever I do this operation of plus 4 and plus 8 in BCD arithmetic. Do you agree? I want to answer in this format. So this is BCD representation of 12. This is BCD of 12, right? This is BCD of 12. Do you agree or not?
Yes, sir.
No. But what we got here from the operation, we got an answer, but the answer is not in the BCD form. This answer is not in BCD form. So how do you make this into BCD form? So we have a small logic here. We have a small logic here. So whenever you are doing BCD arithmetic, so whenever the result is greater than 1010 in binary, whenever the result is greater than 1010 in binary, to get answer in BCD, add 0110 to it. So what I am doing here, whenever the result is greater than 1010 in binary, to get the answer in BCD form, just add 0110 to it. So what is 0110? It is 6, right? It is 6, right? So add 6 to it. So 6 to the result which you got here. So I'll just put 6 to it. I'll just add 6 to it. So what is the answer you get now? So this will be 0 here, this will be 1 here, this will be 0, carry 1, this will be 0 followed by 1. So remaining all significant years, you make them as 0. Now what is the answer you get here? 3 zeros 1 followed by 0, 0, 1. So is it what? Is this value what? Is it in BCD form? Is this in BCD form? Question mark. Answer somebody. Is this in BCD form now? The answer is it in BCD form?
Yes, sir.
Yes, sir.
So what is the answer now in BCD form which we got here? 12 in BCD. So this is an important point you should understand. So whenever you are doing the BCD arithmetic, so whenever the result of the operation is more than 1010 in binary, so what you have to do is to bring the result into the BCD form, just add a 6 in binary to the result which you got there. Yes? Following the discussion. Following the discussion there.
Yes, sir.
Now going further, let us take one more small example here. I do this operation plus 8 plus 9. I do this operation plus 8 plus 9 to make this concept clear. Plus 8 plus 9. What is the answer you get? What is the answer you get? Plus 17. So 8 in the binary BCD is what? 0. 8 in BCD is 1 followed by 3 zeros. 9 is this. Agree? Just add them together. 1, 0, 0. 1 plus 1 is 1, 0. So is this 17 here? Is this 17? Is it in BCD form?
No, sir.
No. So what you do here? So as the result is more than 1010 in binary, so what you do? Just add
0 1 1 1 0.
just add 6 to it in binary. 0 1 1 0. So now check the answer. Remaining most significant is you place zeros. So what is this answer we got here? This is BCD 1, this is BCD 7. So now the answer is in BCD 1. Agree? So in this way, you have to take care of things when you are doing operations in BCD. Okay. Now I give you one small example. So 184 plus 576. Can you do that? 184 plus 576. Can you do this? 184 plus 576. Can you do this addition in BCD 1? And tell me the actual answer in BCD. Somebody can share your screen and show me if you are online. Yes, are you people able to do that? Are you guys able to do that?
Yes, sir.
So what is the answer you get? You get the answer directly in BCD form? 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 Answer my question, man. Do you guys get the answer directly in BCD form? No, right? Obviously, no. So what you add, just add 6 to that so that you get the answer in BCD form like this here, 760. So this is the BCD code, and how do you do BCD arithmetic? Like that, we can have other decimal codes as well. So these are some of the examples for other binary codes which are possible. We call this as 8421 code. So using the 8421 code, you can represent numbers 0 to 9 in this fashion. So these codes which you see here, 8421, 2421, 84 minus 2 minus 1 are called weighted codes. So every place has a weight here. So this place has a weight 1. The second digit has a weight of 2. Third digit has a weight of 4. Fourth digit has a weight of weight of 8 there. So you can get the value of the number by just multiplying the quotient here with the weight there. Okay. So 1 into 2 power 1. 1 into 2 power. So the weight of 1 here is 1. Similarly, see here. Just add the weight, you will get the value of the number. So in this case, remaining 3 are zeros there. So 8 is multiplied with 0, 4 is multiplied with 0, 2 is multiplied with 0, and 1 is multiplied with 1. And add them together, you will get the value as 1. Now, look for the case of 0010. It is in 8421 code, which is an example for a weighted code here. So every digit has a weight associated with it. So in this case, 0 here has a weight 1, this 1 here has a weight 2, 0 here has a weight 4, and finally this 0 here has a weight 8 there. So just multiply the quotient with the weight, corresponding weight, you will get the value of the number. If you do that, you get 1 into 2, that will be 2. So this is called as 8421 code. So any number, we can represent using different binary codes there. One example of binary code is what is called as 8421 code, which is an example of weighted code there. I can have one more weighted code like something like this. 2421 code is also an example for a binary code. Now here also it is a weighted code. You can get the numbers 0 to 9 in this format here. But the problem here is 4 can be represented in 2 ways here. So I can use a third one here to represent 4, or I can use 1011 also 1010 also to represent 4. So in this case, the number 4 has 2 representations here whenever you are using 2421. Similarly, I can have a weighted code like 84 minus 2 minus 1 also for representing numbers there. Okay, so these are examples of what are called as weighted codes here. Weighted binary codes. Okay, every digit has a corresponding weight here. Based on that, you can identify the value of the number. Now, the third column here represents an XS3 code. So what we do in XS3 code is, first we represent the number in the binary. To that you add 3 to it. That will give the value of the number. So 0 is represented as 0 take in binary first. To that add 3 in binary. So that will give the XS3 code of 0. Similarly 1, what you do to represent 1 in XS3, just take the binary of 1 first. To that you add 3 to it. So 1 plus 3 will make 4. So 0100 is the binary code in XS3 for the number 1. Okay, you are following the discussion there? You are following the discussion there. XS3 means first you represent the number in binary. To that you add 3 in binary to it. That you will get the XS3 code for the corresponding number there. Am I clear with the discussion, guys? So in this way, we have different binary codes here. So there can be weighted binary codes, there can be non-weighted binary codes. So if you see from this table here, 8421 code, 2421 code, 84 -2 -1 codes are examples for what are called as weighted binary codes. And if you see here, XS3 code is an example for a non-weighted binary codes. So binary codes, there can be of two types there. One is referred to as weighted code, the other one is referred to as a non-weighted code. Examples for weighted code can be 8421, 2421, 84 -2 -1 codes are examples for weighted codes. And examples for non-weighted codes is your XS3 code, which is shown here for the numbers between 0 to 9. Am I clear with this small table representing the different types of binary codes there, weighted codes and non-weighted codes? Guys, please respond. Guys, please respond. Do you have any doubts here? These things are very important for the further discussion. These things which I am discussing now are very important. Binary codes are very important for further discussion. Any doubts here? Any doubts here? Are you guys there? So any doubts here? Difference between weighted and non-weighted codes. Difference is clear?
Yes, sir.
Now going further, there are other examples there. So using 4 bits, there are possibility of a 2 power 4, that is 16 combination. But we are only representing the first 10 combinations. Therefore, 6 more are unused binary combinations there, which are not used there, not represent the decimal digits. Okay. So using 4 bits, you can represent a maximum 2 power 4, that is 16 binary combinations. So of the 16 binary combinations, we are using only the first 10 binary combinations using to represent the decimal digits from 0 to 9 here in this table. Okay. Now, so BCD 2421, 84 -2 -1 codes are examples for weighted codes. In weighted code, each bit position is assigned a weighted factor there in such a way that each digit can be evaluated by adding the weights of all the ones in the coded combination. Okay. So this is how you define a weighted code there. I will illustrate that with respect to an example there. And XS3 code is an example for a non-weighted binary code. Okay. Now, the point here is one more important definition here. 2421 code and XS3 codes are examples of self-complementing codes. So why they are referred to as self-complementing codes is such codes have the property that the 9th complement of the decimal number can be obtained directly by changing 1s to 0s and 0 to 1. So in this scenario, in these two codes, what you can do is you can get the 9th complement of the decimal number by just interchanging 1s with 0s and 0s to 1. That is the reason why 2421 code and XS3 code are examples for self-complementing codes. Please understand this term called self-complementing. So 2421 and XS3 codes are examples for self-complementing codes where the 9th complement of a decimal number can be obtained by simply interchanging 1s with 0s and 0s with 1s there. Am I clear till this point? So I have an example here. So 395 you can represent in XS3 as 0110 followed by 1100 followed by 1000 there. If you take the 1's complement of this, that will be this value here. So this is nothing but 604. So 604 is nothing but the 9's complement of 395. So that is the specialty of these two codes, which are self-complementing codes. 2421 code and XS3 codes are examples for self-complementing codes. Please understand this term. Okay, so XS3 code is also an example for non-weighted code. And we have one more important code called as gray code. So gray code is very important whenever you are representing continuous or analog information in a digital representation. Okay, so frequently what happens is all signals are continuous signals. So in order to represent continuous signals, we use a special kind of code which is called as gray code. So the specialty of this gray code is, let me try to illustrate how do you get the gray code first. So please understand here how to get the gray code. So if you are using a gray code with only 2 bits, so there will be 2 bits here. So I'm starting with the least significant bit 0, 1. The next will be 1. So in this case, you see here, from this number, this code to this code, how many bits are changing? This is gray code representation of using 2 bits. So from this number to this number, how many bits are changing? Only 1 bit is changing. Only 1 bit is changing. So I can use this kind of a representation for whenever you want to represent continuous signals. Okay. Say for example, 3 bits you consider. So 3 bits, I'll take something like this. I'm taking the mirror image of it. 0, 1 followed by 1, 0, followed by 0, 1, followed by 1, 0. Okay. Then what I do? I take 2 zeros here, followed by 2 ones. Then I take 2 ones, followed by 2 zeros, which is the mirror image. Okay, can you see? For the second column here, this is the mirror image. Okay. Similarly, the third column, what I do? I put 4 zeros, followed by 4 ones. Now, what do you observe from if you go from one pattern to the other? How many bits are changing? To go from this pattern to this pattern, how many bits are changing here? Only one bit is changing. Do you agree? To go from this pattern to this pattern, how many bits are changing here? How many bits are changing?
1 bit.
1 bit is changing. So if you go from this pattern 0, 1, 1 to 0, 1, 0, how many bits are changing? How many bits are changing? Only 1 bit is changing. So this is the specialty of gray code. So as you progress from one binary pattern to the other, only 1 bit in the combination changes there. So that is the specialty of gray code. So I have illustrated here how to represent the gray code using 3 bits here. So what you do, start from the least significant bit position, put a 0 first, followed by 1. Take the mirror image of that. So what will be the mirror image of that? 1, 0. Now once again take the mirror image of that. That will be 0, 1. Once again take the mirror image of that. That will be 1, 0. Do you agree? You agree? How I wrote the last column? Yes? Now, go for the next column. What you do? You started initially with 1, 0, followed by 1. Now you begin with 2 zeros, followed by 2 ones. Take the mirror image of that. Okay? 2 ones, followed by 2 zeros. Am I clear? Second column, how I got? Am I clear? Second column, how I got? Guys, you are following the discussion or not?
Yes, sir.
Now, in the second column, I started with 2 zeros, followed by 2 ones. Now start with 4 zeros, followed by 4 ones. So this will be the 3-bit gray code. This will be the 3-bit gray code of binary combinations. Okay. Now, if you observe here, from every pattern to every pattern, there is only 1 bit change. That is the specialty of gray code. So whenever you want to represent continuous values of signals, Okay. So the most possible frequently used binary code system is possible binary code which we can use is gray code. So now you should know how to write a gray code for 3 bits, how to write a gray code for 4 bits. Am I clear with that understanding? Say for example, I want to write a gray code for 4 bits. How do you do that? Start with the least significant column. Start with 0 followed by 1. Take the mirror image, 1 followed by 0. Take the mirror image, 0 followed by 1. Followed by mirror image, 1 followed by 0. Mirror image. Like that. You are following? Can you do that? Can you do that, guys? Can you write the 4-bit gray code now? 4-bit gray code will have how many binary combinations? Anybody? 4-bit gray code will have how many binary combinations? Anybody?
16.
16 combinations. So what you do is just after this discussion, just write the possible 2 power 4, that is 16 binary combinations of the gray code, and show it to me in the next class. I'll ask one of you to show the 4-bit gray code in the next class. Okay. So with this discussion, let me stop the discussion for today. Remaining things we'll see in the coming class. Let us stop the discussion here. Let me download the attendance. So thank you guys. I'm stopping the recording as well.